The title of this presentation is Modeling Multilayer Graphene with Coupled Pendulums. I am from the Energy Research Institute of Budapest. The outline of the presentation is as follows. First, we will talk a little bit about the wave packet dynamics because we are going to use that method in our calculations. Then we show the construction method of the multilayer graphene pseudopotential. We present how to verify the pseudopotential for different multilayer graphene structures. Using this potential, first, we analyze the wave packet hopping in bilayer graphene structures with different stacking. Then we go on to study the ABC trilayer rhombohedral graphene. In the end, we present a classical mechanical system, the coupled pendulums, whose dynamical behavior is similar to the above-mentioned multilayer graphenes. This presentation is based on a research paper, which was recently published in the journal Carbon Trends. The title of this paper is New Local Pseudopotential for Multilayer Carbon Materials and its Application in Wave Packet Dynamics. This work was performed in Hungarian-Belgian cooperation, which has been existing for more than 25 years. The work was supported by the Graphene Flagship Program of the EU. Wave packet dynamics is actually a scattering experiment in the computer. We have an incoming wave packet, and we have a system, a black box on which it is scattered, and then we have a scattered wave packet. The wave packet can be scattered in different directions, with different amplitudes and phases. We symbolize this with arrows of different thicknesses and directions. The two input parameters' initial conditions are the initial wave function and the potential, which describes the system. Then, the magics of the wave packet dynamics provides the time-dependent wave function. We can then calculate everything from the time-dependent wave function, since it represents the state of the system, which is why it is called a state function. We can, for example, calculate the probability density, the probability current density, and various eigenenergies and eigenfunctions. In this slide, we demonstrate the power of wave packet dynamics on a simple one-dimensional model. We have here a toy model of a crystal, which is constructed from 10 equidistantly placed sharp potential barriers. The incoming wave packet is a Gaussian, and these snapshots show the time development of its probability density. But, according to the quantum mechanics of periodical systems, there are allowed and forbidden energy bands of a periodical potential. If the energy of the incoming wave packet falls into the allowed band, as in the left column, the wave packet goes through the periodic potential. But if the energy falls into the forbidden band as shown in the right column, then it is reflected. This is already a two-dimensional demonstration. We study here a textbook example, scattering on a radial symmetric potential. We know from elementary scattering theory that the scattering will be radially symmetric in this case. The incoming wave packet is a narrow Gaussian, but the outgoing wave packet is the superposition of a circular symmetric part and the incoming wave packet itself. Similar, circular wave fronts are seen in the case of water waves, scattering on a circularly symmetric obstacle. The upper row shows the snapshots of the time development of the probability density, and the lower row shows the snapshots of the time development of the real part of the wave function. It is interesting to note here that the phase velocity and the group velocity of the wave packet are different. In the recent years, we developed an interactive computer program, Web Schrödinger, for the study of two-dimensional time-dependent and time-independent stationary quantum phenomena. The program itself runs on our server and can be used through the internet with a simple web browser. Nothing is installed on the user's computer. The user can load, run, and modify ready-made example files, or prepare own configurations, which can be saved on for later use. This software is available from our webpage www.nanotechnology.hu. The examples include quantum tunneling, simulation of a scanning tunneling microscope, eigenstates of rectangular and circular potential walls, harmonic oscillator, molecular orbitals, and many more. A full, three-dimensional wave packet dynamic simulation, however, needs a considerable amount of computing power. But this calculation is well parallelizable, and hence it can benefit a lot if we run it on a GPU graphics processor instead of the CPU. Indeed, we measured a 50 times speedup in the GPU version of the three-dimensional wave packet dynamical calculation. This work was performed as a prize-winning graduate student project. The three-dimensional example, shown in this animation, is the scattering of a wave packet on a two-dimensional lattice of spherical potential barriers, as an analogy of an optical lattice. We see a diffraction phenomenon here. The wave packet is scattered in certain directions dictated by the Bragg rules. We briefly show the computation method used in our wave packet dynamical simulations. We want to solve the time-dependent Schrödinger equation here, which is a partial differential equation. This can be accomplished by writing down a formal solution and putting the Hamilton operator into the exponent. With this, the time dependence of the wave function can be expressed as the effect of the U propagator, or time development operator, on the initial wave function. The problem is that it is not easy to calculate the operator exponential. In the case of the simplest approximation, the Hamiltonian is a sum of a kinetic energy part and a potential energy part, and, moreover, the potential is local. But even in this simple approximation, the commutator of the kinetic and potential energy operators is not zero. Hence, we use again an approximation here by expressing the operator exponential as a symmetrical unitary product. Then the time evolution operator is split into three consecutive steps: a free propagation for time delta t per 2, a potential only propagation for time delta t, and again a free propagation for time delta t per 2. The kinetic energy operator is calculated in momentum space by calculating the momentum space wave function by fast Fourier transform. Convergence towards the exact result is obtained by using a small delta t, but it is an important advantage of this method that it preserves the norm of the wave function, and it is exact if the V potential is zero. We are going to apply the new pseudo-potential to multilayer graphene. But first, a few words about what graphene is. Graphene is known to every child who has ever written with a pencil or drawn with charcoal. Graphite is a layered material. Within the layers, there is a strong covalent bond between the atoms, but between the layers, there is only a weak van der Waals bond. Therefore, the layers can easily get peeled off when the pencil is dragged across the paper. In this case, graphene layers come off, and this is actually how we write with the pencil. These two Manchester researchers received the Nobel Prize in 2010 for the production of graphene. The properties of multilayer graphene depend on how the layers are offset from each other. Different layer offsets are presented here. In the case of A stacking, the atoms of all the layers are below the other. In the case of a B stacking, every second layer, the B layers, are offset compared to the A layers. In the case of ABC, we have 3 layers with a gradual shift, and in the turbostratic case, we are talking about random layer shifts. It is interesting to note that this is how the diffraction pattern changes with random layer shifts. If the layers are completely under each other, we have a diffraction image consisting of discrete peaks. But the peaks are broadened horizontally with randomizing the stacking, and we get vertical lines if we shift the layers randomly relative to each other. The periodicity in Z direction is different in the AA, AB, and ABC cases. In the case of AA stacking, if the layers are under each other, the periodicity of the crystal structure in the Z direction is equal to the layer spacing C. In the case of a B stacking, every second layer is the same, so here the periodicity is 2C, and in the case of ABC, it is already 3C. In the turbostratic case, we can speak of a non-periodic system. The Z periodicity is infinite. To perform a wave packet dynamical simulation of a given physical system, two input functions must be given: the initial wave function and the potential. If we want to construct a pseudopotential for multilayer graphene, this pseudopotential must correctly describe both the atomic structure and the electronic structure of multilayer graphene. The functional form of the pseudopotential is the sum of four anisotropic Gaussian functions centered on each of the atoms. The anisotropy means that we allow for different parameters in the XY plane and in Z. So, we consider parametric potentials with 12 parameters. Then we variationally optimize these parameters to match the real band structure. So, our band structure calculated from the trial pseudopotential also has 12 parameters, and in the end, we have to find a parameter set where the band structure calculated from the pseudopotential best approximates the real, in this case, the tight binding graphene band structure. The delta difference between the variationally calculated and tight binding calculated p-energy bands are minimized using the Monte Carlo technique. In our case, our goal is the multilayer graphene band structure. These three figures below prove that our approach was successful. The first figure shows the result applied to a single carbon atom. This is what the in-plane potential looks like, and this is how the potential perpendicular to the plane looks like. The potential is indeed anisotropic. Figure B shows that the pseudopotential indeed reproduces the band structure. In the graphene band structure, we see here the linear crossing of the two bands at point K. And in figure C, we see the orbitals themselves, the wave functions. It can be seen that these orbitals are really pi states. The probability density is 0 in the plane of the graphene, and the maxima are located below and above the plane of the graphene. Green is the positive part of the wave function, and red's the negative part. The maximum of the wave function is approximately 0.7 angstrom above the graphene, as proven by ab initio calculations. This pseudopotential nicely describes the band structure of graphene. Since graphene is a periodic two-dimensional crystal, the Bloch theorem also applies to it, so the phi wave functions are given as a product of a plane wave part and a lattice periodic part. Here we plot how these parts look like for different wave numbers. At the K point, this is the plane wave part, this is the UF function, which is lattice periodic, and this is the phi wave function itself. Using our pseudopotential, we examined the electronic band structures of various typical graphene and graphite structures. The first row shows bilayer and trilayer graphene structures, and these are infinite layer systems with the same stackings. The figures show the band structure of these graphene systems in the vicinity of the K point. These results agree nicely with those seen in the literature, where the band structures of these systems were calculated using density functional methods. Here we examined how the graphite band structure, infinite graphene layers, depends on the Z component of the wave number vector when we calculate it from our new pseudopotential. So now we go perpendicular to the plane of the graphene in momentum space. Here, The KH band structure is shown for the two stackings. This figure also matches nicely with what we can see in density functional calculations. This figure proves that the new pseudopotential even describes the effect of the electric field nicely. Here we see tri-layer rhombohedral graphene, to which we applied a perpendicular electric field. And here we show how the band structure changes. The solid line is when there is no electric field, and the dashed line is when there is an electric field. You can see that a forbidden band, a gap, is opening. The magnitude of the electric field is 0.2 volts between A and C, between the two extreme layers. So, finally, we can conclude that our newest pseudopotential can describe multilayer graphite and graphene very well. This slide shows how we apply the new pseudopotential to model multilayer graphene systems in a VPD calculation. In these multilayer graphene systems, we can change the number, offset, and rotation of the graphene layers, and we can also introduce defects. Technically, what we do is that we start the wave packet from a single layer graphene surface, and it flows into the multilayer region. Then we examine how the wave packet behaves there. We expect that because of the weak van der Waals coupling of the two layers, the electronic wave packet will bounce back and forth between the two layers, as shown schematically in this figure. The blue arrows show the three-dimensional coordinate system applied in our calculation. The system is periodic, infinite, in the x direction, as shown by these brown dots. The initial momentum of the wave packet, shown by this green arrow, points in the y direction perpendicular to the region 1-2 boundary. Now that we have the potential, we still have to construct a suitable initial state for our VPD calculation. In the case of our earlier VPD calculations, we used a simple Gaussian wave packet as the initial wave function. Those calculations were, however, made with the Jellium approximation for the pseudopotential. Hence, the potential was constant in that region of space where the wave packet started from. The eigenstates of a constant potential are plane waves. That's why a Gaussian superposition of plane waves was a perfectly suitable initial condition. This is not the case here, where the wave packet starts from a region with periodic potential, because the graphene wave functions are not simple plane waves, but plane waves multiplied by a lattice periodic function, as the Bloch theorem states. Hence, we first calculated the Bloch functions of graphene, using our pseudopotential for different k vectors along the y direction in momentum space. We want to construct a Bloch wave packet, a wave packet constructed from graphene eigenfunctions. This can be accomplished by applying a superposition of the eigenfunctions with different k-wave vectors, utilizing a Gaussian kernel. The resulting Bloch wave packet is infinite in the x direction, but has a finite half-width in the y direction. When we calculate the time development of this Bloch wave packet on a pristine graphene surface modeled by the multilayer graphene pseudopotential, we can see that the wave packet propagates in the -y direction. Note that there is only a very little dispersion, that is, the shape of the wave packet increases only very slowly. This is because of the linear dispersion relation of the p states of graphene near the k point. In principle, there should be no dispersion at all, but a small dispersion occurs because of the finite size of the wave packet, which corresponds to a finite momentum distribution near the k point. Going away from the k point, however, the dispersion relation is not any more strictly linear. This animation shows what happens when we introduce a circular defect potential. The wave packet is scattered on the defect. Note that the scattered wavefront has a hexagonal symmetry. This scattering phenomenon involves scattering between K and K prime states, which is called intervalley scattering in the theory of graphene. We can often see signatures of the intervalley scattering on Fourier transformed scanning tunneling microscopy images of the graphene surface. Now we have all the necessary ingredients and tools to examine our expectation that the electronic wave packet bounces back and forth between the two layers in a bilayer graphene system. This animation shows the time development of a constant probability density surface of the wave packet. The isodensity surfaces are composed of closed 3D objects around the local maxima of the probability density with nearly spherical shapes. Note the p character of the orbitals in this figure. The isoprobability surface has two layers of maxima below and above the graphene sheets, corresponding to the two positive and negative lobes of the pi orbital. In region 1, when the VP is still on single-layer graphene, we can see only 2 sheets of maxima, but there are 4 sheets of maxima in the bilayer region, region 2. The probability density is changing in the y direction. Hence, the size of the isodensity spheres is also changing along this direction. When the VP reaches the region 1-2 boundary, it penetrates into the 2-layer region and begins to hop between the layers. Note, however, that this simulation was performed for AA graphene when the atoms of the adjacent layers are exactly below each other. The situation is slightly different for the Bernal graphene when the A and B layers are displaced with 1 atomic distance. Here, only half of the atoms has another atom below them in the adjacent layer. In the case of Bernal bilayer graphene, the animation reveals a backscattering at the boundary between the single layer and bilayer regions, and also a changing of the atomic scale pattern. This next series of animations shows the VP time development on the 2-layer graphene using another visualization technique, where we projected the probability density of the pi orbitals onto the graphene plane. This was accomplished by integrating the probability density in Z for both graphene planes. The resulting 2D probability density is rendered on a false color scale. The dark blue hexagonal mesh is the pseudopotential. The 2 bright bars are the initial wave packets at time 0 femseconds. When we start the animation, we can see the hopping between the layers and the differences between the 2 graphene versions. There is no backscattering in the AA case, but we see a backscattering in the AB case. When we zoom onto the single double-layer boundary region, we can see better how the atomic scale pattern is different for the AA and AB stackings. These snapshots taken at 0, 7, and 14 femtosecond show important moments of the VP time evolution. Here we plot the 2 layers side by side in a 2D plane, but in reality, they are under each other. In the beginning, the VP is in region 1 on single-layer graphene. At 7 femtosecond, it already penetrated the barrier, and some of it hopped onto layer 2. Then, at 14 femtosecond, we see a backhopping onto layer 1. In the case of the Bernal configuration, the process is more complicated. There is a backscattering, very well seen in 14 femtosecond. And the atomic scale pattern also does change. These phenomena are also seen in the isodensity surface rendering, shown here. The time development of the Bloch VPs occur in two distinct length scales. There are changes on the atomic scale wave function, the UF factor of the Bloch function, and there are changes on the 10 angstrom scale, superpositions with different amplitudes and phases of the exponential factors of the Bloch functions with different k values. The behavior of the VP in the two spatial scales are, however, not independent. When this VP is evolving on a pristine graphene sheet, the momentum distribution remains constant, but the phases of the components are slowly changing in time with different speeds, because the dispersion relation is not linear away from the K point. Hence, the width of the VP is slowly increasing, but this spreading is considerably slower than for a VP propagating in free space, where the dispersion relation is quadratic. When the VP enters into region 2, in the case of AA graphene, we do not see any backscattering at the boundary and the shape of the atomic patterns remains seemingly unchanged, which means that only intra-valley scattering occurs in this case. The case of the AB graphene is different. There is a considerable amount of backscattering at the interface. This indicates the presence of intervalley scattering, the emergence of states at the opposite K point, which means a momentum in the opposite direction. Consistently with this observation, the atomic scale pattern is also changing, caused by the interference of the Bloch waves at the two opposite K valleys. In order to study the long-range behavior of the wave packet, we filtered out the atomic scale details by a low spatial frequency convolution filter. This slide shows the long-range time domain behavior of the wave packet on two-layer graphene as a color-coded space-time density map. Figure A is the side view of the calculation scheme with the two graphene layers, shown in blue and yellow. Figure D shows the color map. White corresponds to 0 probability. Blue is when the wave packet is on layer 1, yellow when it is on layer 2, and dark gray when the probability density of the wave packet is equal on both layers. The Bloch VP starts at region 1, the single-layer region from position Y0. During the initial phase of the time evolution from 0 to 5 femtoseconds, the VP propagates towards the boundary of region 1-2 in the plus Y direction. Note that the width of the VP remains nearly constant due to the nearly linear dispersion relation in the vicinity of the K point. Upon reaching the boundary at Y1, the VP propagates into region 2 and begins to oscillate between the two layers, seen by the alternating pattern of blue and yellow colors. The oscillation pattern is simple for the AA graphene, but we see a complicated behavior for the AB case. There is a considerable resonant reflection on the boundary, shown by the blue color in region 1 at t greater than 5 femtoseconds. The vertical yellow band around Y1 means that there is a localized state at the boundary. A part of the wave packet is trapped on the edge atoms of layer 2. How can we explain, preferably not only qualitatively, but quantitatively, this bouncing of the wave packet between the two graphene layers? It is conceptually easy for AA graphene when the two layers are completely identical. Just look at this pair of graphs. The left figure shows the p-band structure of single-layer graphene, and the right figure is the band structure of the B layer. A level splitting occurs. The states are two-fold degenerate. This means that for each eigenvalue, that is, for each energy, there are two different eigenvectors, that is, two wave functions with slightly different k-Bloch wave numbers. This means that we have two harmonic functions with slightly different wavelengths, and this causes a beating phenomenon with spatial frequency delta k. This beating phenomenon is analogous to the behavior of a pair of identical pendulums coupled by a weak spring. As is well known in classical mechanics, Such a system has two vibration modes. In the first mode, the two pendulums move in phase. Hence, the length of the connecting spring doesn't change. Hence, the frequency of this mode is the same as the swinging frequency of an isolated pendulum. In the second mode, the two pendulums move in opposite phase. When they move towards each other, the spring repulses them, but when they move apart from each other, the spring attracts them. This means that the eigenfrequency of this opposite phase mode is larger than that of the in-phase mode. The general motion of the two pendulum system is a superposition of these two modes, and in that motion, the energy is constantly swinging back and forth between the two pendulums. In other words, the root cause of the hopping is the fact that the single-layer wave functions are not eigenstates of the B-layer Hamiltonian. In the remaining portion of this talk, we are going to examine the spectral behavior of the wave functions. One single wave packet dynamical calculation provides us with the behavior of all the energy components contained in the spectrum of the VP. By the help of the time-energy Fourier transform of the time-dependent wave function, we can access these individual spectral components. Both the time domain and the energy domain representations of the VP behavior has its advantages and disadvantages. If we want to know the dynamics of the system exactly, we can accomplish this only with a finite energy resolution. But if we want to know the energy exactly, we can't have precise dynamics. This uncertainty is because of the time-energy uncertainty relation, which says that delta E times delta T can't be smaller than h bar over 2. This slide shows the long-range behavior of the different energy components of the VP on bi-layer graphene for the two stacking configurations as color-coded space energy density maps. The calculation of the energy and position-dependent probability density is similar to the space-time density map, but using the energy-dependent wave functions instead of the time-dependent ones. The case of a graphene is relatively simple. The most important phenomenon is the oscillation of the VP between the two layers, alternation of the blue and yellow colors. The spatial period of this oscillation monotonously decreases with increasing energy. In the case of the AB graphene, however, the energy dependence of the hopping distance is much more complicated. This is a region of middle energy, where the amplitude of the hopping is small and a strong backscattering is present, shown by the finite probability of finding the wave packet to the left of its starting point. But going away from the middle region in energy, we see no such backscattering, and the hopping amplitude is much larger. Here, on figures D and E, we show the spectral decomposition of the two-layer wave functions in terms of the one-layer wave functions. This is a generalized Fourier transform, where the basis functions are the single-layer graphene states. This scalar product basically reproduces the band structure of the simple hexagonal and Bernal graphene, but backscattering bands are not excited in the case of simple hexagonal graphene. However, they are weakly excited in the Bernal stacking. For the case of the AA graphene, the delta K splitting monotonously increases in our energy window. This explains the monotonous decrease of the hopping distance. In the case of Bernal graphene, there is, however, a band crossing at -3.1 electron volts. Delta K is 0 here, and it slowly increases until the band edge, E4. Hence, the hopping distance is infinite at -3.1 electron volts and decreases until E4. We see another scenario near the Fermi level, between E4 and E8. There is only one plus K branch, but there is a weak minus K branch. These are shown in red. In this energy region, the interference of these states determines the hopping between the layers. We can observe two features here. First, delta K decreases to 0 when approaching EF from either below or above. Hence, the hopping distance diverges when approaching the Fermi energy. Second, the amplitude of the hopping is small because the minus K block components of the VP have a considerably smaller amplitude than the plus K components. The two parabolic bands meet at the Fermi energy, which is E6 in this figure. Hence, the band structure is locally flat at this point. As we can see on subfigure C, there is a considerable amount of VP reflection on this energy level, as shown by the large probability to the left of I0, seen as a blue bar on C, since I0 is the point from where the wave packet started, the presence of a finite probability to the left of. This point signifies a reflection. Figures F and G show horizontal line cuts of the space energy density maps. These are position-dependent wave packet probability densities for the two layers at different energy levels. Blue is for the first layer, yellow is for the second layer. For the case of the simple hexagonal graphene, the hopping distance monotonously increases in our energy window. In the case of the banal graphene, we can observe that the amplitude of the hopping is small in the small energy region, denoted by this red ellipse, because the minus K components are considerably smaller than the plus K components. At the Fermi energy, the band structure is locally flat. The VP can tunnel into region 2, but cannot propagate there because of the zero value of the group velocity. Note the linear decay of the probability density in region 2. There are also some edge states at the leading edge of layer 2 in some energies, represented by black spots on the space energy density maps. The large probability density is high-clipped at the point Y1 on the line cuts. The edge states cause strong forward and backward scattering, seen as interference oscillations at these energy levels on the space energy density map. After gaining some confidence from the good performance of the new pseudopotential for the B layer, we go on to explore wave packet dynamics on ABC rhombohedral trilayer graphene, where we have 3 layers with a gradual shift. By applying the shift again to layer C, we arrive back to the A configuration. Thus, the periodicity is 3C. As we can see, the band structure of this material is complex, having a flat band at the Fermi energy and 2 parabolic conduction and valence bands, with band edges a little away in momentum from the K point, resulting in total 3 bands away from the Fermi level. We performed a wave packet dynamical calculation followed by a time-energy Fourier transform for the rhombohedral graphene, in a similar setup as for 2-layer configurations. Just the region 2 now has 3 graphene layers instead of 2, each displaced relative to the next in an ABC configuration. Here, we show the long-range behavior of the different energy components of the VP. That is the normalized probability densities for the 3 layers as a color-coded position energy map. We utilized the cyan-magenta-yellow subtractive color system. Each YE pixel is colored cyan, magenta, and yellow when the VP is on layer 1, 2, and 3, respectively. Normally, on a 2-dimensional paper or screen, the position of each pixel can represent only 2 variables, say X and Y. But in grayscale imaging, the darkness of the pixel provides a third Z coordinate. If we want to code even more information into the pixels, we can use color. The theory of trichromatic color vision, the Young-Helmholtz theory, postulates the existence of 3 types of photoreceptors in the human eye, with different but overlapping response to different wavelengths of visible light. The relative strengths of the signals detected by the 3 types of photoreceptors are interpreted by the human brain as a visible color. This makes us possible to visualize the relative magnitude of 3 different quantities as a color of each pixel. The 2 most widely used color systems are the RGB, red, green, blue, used in screens. It is an additive color system, and the CMY, cyan, magenta, red, used in printing, which is a subtractive color system. CMY colors are the negatives of RGB colors. This figure is an illustration of the CMY color system. It demonstrates the concept of the subtractive color mixing by visualizing a displaced stack of cyan, magenta, and yellow-tinted glass discs, illuminated by white light from below. The center of the figure, where all 3 plates overlap, blocks all colors. Hence, it is black. The saturation of the CMY colors are changing gradually as a function of 3 quantities. Row 1, 2, and 3. Each color correspond to a given combination of the 3 probability densities. Hence, a given color on the space energy density map represents the distribution of the probability density between the 3 layers at that particular energy and position. As special cases, the color is white when all the 3 densities are 0 and black when all the 3 densities are 1. These figures show the probability densities at fixed energies, marked E1 and E2. These 2 energies are in the region where all the 3 bands exist, that is, above and below the energy region, where only the flat band occur. Note that while row 2, the probability density for the middle layer is a periodic function. See the magenta curves here and here. The row 1 and row 3 probability densities for the upper and lower layers are not periodic, as seen on the cyan and yellow curves. We can understand this dynamical phenomenon by the help of a simple classical analog, the 3 weakly coupled mathematical pendulums. The dynamical behavior of that system is indeed similar to the trilayer graphene, because in both cases we have 3 identical oscillators coupled by a weak interaction potential. We have 2 edge pendulums corresponding to the 2 outer layers of the trilayer structure and 1 inside pendulum corresponding to the middle or bulk graphene layer, which is connected to both outer layers. This slide shows the 3 eigenmodes of the 3 weakly coupled pendulum system. In the first mode, the 3 pendulums move together, hence the springs do not influence the motion. The frequency is the same as for isolated pendulums, omega 0. In the second mode, the 2 outer pendulums move in opposite phase, and the inner pendulum is at rest. In the third mode, the 2 outer pendulums move together, and the inner is in opposite phase, but with twice as big amplitude. The general motion of the 3 pendulum system is the superposition of the 3 normal modes, where C1, C2, C3 are arbitrary complex constants. These determine the relative phases and amplitudes of the 3 eigenmodes. In the 3 coupled pendulum case, we have 3 incommensurate eigenfrequencies. That's why the motion of the 2 side pendulums is aperiodic. But the 3 corresponding eigenvectors are such that for the case of the middle pendulum, one of the eigenvectors have a 0 component. Hence, for the middle pendulum, we have only 2 eigenfrequencies that can interfere. This is the cause of the quasi-periodic motion of the inner pendulum. The detailed form of the time dependence of the motion depends on the strength of the coupling and the relative amplitudes and phases used in the superposition of the 3 eigenvectors. But already, without a detailed fitting, we can see that the functions describing the dynamical behavior of the 2 very different dynamical systems, 3-layer rhombohedral graphene and 3 coupled pendulums, are indeed similar. The term free body problem is sometimes used in the more general sense to refer to any problem involving the interaction of three entities. Historically, the first specific three-body problem to receive extended study was the one involving the Moon, Earth, and the Sun in celestial mechanics. The three-body problem is a special case of the n-body problem. Unlike two-body problems, no general closed-form solution exists, as the resulting dynamical system is chaotic for most initial conditions, and numerical methods are generally required. The motion of three bodies is generally non-repeating, non-periodic, except in special cases. This inherent instability of the three-body problem makes the present situation of the world dangerous. During the second half of the 20th century, the world had two superpowers, the US and the Soviet Union. Today's world has three nuclear superpowers, the US, Russia, and China, and this makes the international situation much more unpredictable as before. There are similar works where people saw long-range quasiparticle oscillations in two-layer and three-layer graphene structures. For example, in this nanoletters paper from 2013, the authors used twisted bilayer graphene as a model of a well-known phenomenon in particle physics, the neutrino oscillation. This second paper from 2019 is a wave packet dynamical calculation for twisted bilayer graphene, but their method is different from our. These authors used tight binding wave packet dynamics, but they also saw neutrino-like oscillations of the probability density between the two layers, shown in blue and red in this figure. Both their calculated probability density and probability current shows an anisotropic hexagonal pattern in agreement with our earlier calculations. This third, recent paper is an experimental study of Friedel oscillations seen by scanning tunneling spectroscopy on rhombohedral, three-layer graphene structure. Their results are very similar to our calculations, but they measured only near the Fermi energy. Figure E is a contour plot of spatially resolved tunneling spectra recorded along the arrow shown in Figure A. These measurement results are indeed similar to our calculated space energy-dependent probability map in the vicinity of the Fermi energy. The amplitude of the oscillation is decreasing with the distance from the step edge, and the hopping distance is increasing as approaching the Fermi energy. This theoretical paper models some aspects of the two-layer graphene band structure with a simple classical mechanical model using coupled oscillators, as we did in our paper. They formulate an open question here. Is it possible to develop a systematic construction of mechanical systems emulating band structure effects? The pseudopotential presented in this paper can open new ways to investigate electron dynamics in more heterostructures. With small twist angles, since wave packet dynamics calculations can handle large systems with tens of thousands of atoms and thus resolve the bottleneck of the ab initio calculation. We plan to study these Moore systems, such as magic angle bilayer graphene, or stacking faults in rhombohedral graphite with the new pseudopotential as future work. Application of graphics processors can significantly speed up the calculation because the split operator Fourier method of wave packet dynamics is well parallelizable. This method also makes it possible to study magnetic effects by simply including a vector potential term besides the scalar potential. Electron correlation effects play an important role in flatband systems, and also far from the Fermi energy, where the one-electron approximation breaks down. Hence, we plan to account for correlation effects in our calculations in the future. As we presented here, the new pseudopotential nicely describes the electronic and transport properties of various multilayer graphene heterostructures. As a more ambitious program for the future, We plan to develop similar local pseudopotentials for heterostructures, layered structures constructed as stacks of different materials. Different two-dimensional materials have a wide range of properties. They can be metallic, semiconducting, insulating, magnetic, topological insulators, etc. Building such heterostructures, a nano-Lego, can provide us with material systems with predetermined properties. The wave packet dynamical investigation of such materials would give us deep insight into the electronic and transport properties of practical devices fabricated from such heterostructures. Thank you for your attention.